be telling you to rush if we need that. I'm going to be conducting. So thank you very much. And thank you for your patience.
Yes, we're going to do now, in 1 more minute, a test with all the channels active for languages. I just would ask Cristina, and because I think that's the account that you're going to use for to translate, to rename you. I'm checking on the streaming. Yes, we're ready.
Tanya, I am an interpreter in the one you can see int in the front.
Yes. Okay. Yes, you're right, Christina. Perfect. Okay. And we do the test. Okay, interpretation. We have Marise, Cristina, Portuguese, and we have in English.
Eduardo, a question. NSF's NOIRLab, is it, do I have to say NOIR or NOIR?
It's NOIRLab.
NOIRLab. Okay,
NOIRLab.
perfect. Thank you. NOIRLab.
You're welcome.
Pauline is not here yet, right, Trinidad?
Sorry?
No, but she's coming in any minute.
Okay, thank you. No, I'm just asking about.
She's coming in any minute.
It's okay.
And we need Lucas, Jim, and Howard. I don't know if they're gonna test as well.
Okay, let's do the test. I will now activate the channels, so you won't be able to talk to us, and ready.
Okay.
But if you want to start.
Good day to all of you, and welcome to the first event of the Americas Research and Education Networks, bringing the universe to you. These days, due to the challenges that this pandemic has imposed us, it's more important than ever for national research and education networks to connect. The CEOs of CANARIE in Canada, Internet 2 in the United States of America, and RedCLARA in Latin America formed a common goal to work closely together and to highlight the research and education enabled by our network infrastructure and share expertise across the Americas. With that goal in mind, a team of staff...
Dans ce but, une équipe de 3 organisations prévoit des rencontres périodiques pour faire le point sur ce que nous faisons, qui nous
Ana,
Gracias, Ana. Estamos listos, funcionaron todos los canales súper bien. Creo que, I'm sorry, everything works pretty well. I think we're ready with that. French, Spanish, Portuguese, they are all working well. So we are ready with that. We will just wait for the others, for 2 more speakers. And of course, I'm sending email.
Yes, and Pauline told me that she came in and she just left for a second, but she's coming back.
Okay.
Luis, I've got a question for you, Luis da Costa.
Yes.
Your surname is Luiz Nicolaci da Costa, or you rather be named as Luiz da Costa?
Luiz da Costa is fine.
Perfect.
Você prefere se chamar Luiz da Costa?
Luiz da Costa.
I'm listening to the interpreter here.
Yeah, me too.
I don't think I'm supposed to, right? Otherwise, I will get
Sorry,
confused.
I didn't realize that you canceled the interpretation, and I thought it was my turn to try. Sorry.
No,
It's okay, Christina.
I was just wondering if we were having a shadow speaker here behind me.
Oh. Bit nervous.
And I have one question. The presentations that I have from you, Luis da Costa and Eduardo, is the final version, or would you make some change, or did you make changes to it?
Just slightly, just a few changes, but not much.
Okay, it's just because I would like to ask your permission to
I'll send you afterwards. I'll send you afterwards.
Okay, to have them for consultation.
Okay.
I did some concepts and the list at the end to the acronyms. That's all that I did, but the slides are the same. I will send you the update, Tanya.
Thank you. Thank you.
Good morning, Lucas. Such a long time without seeing you. Your microphone is off.
It's because I didn't have.
Tanya did it.
Yes, now you can open it. I'm sorry.
Person.
Okay. Yes.
Hola.
Yes. I mean,
Anya?
yes, it's been a long time that
Very long
we've been
time.
working together.
Yeah.
Yeah, I'm glad to be in touch again. Yeah, Tanya, what I sent you earlier is the latest version that I'm also going to present of the slides.
Okay. Perfect. Thank you very much. ¿Y es Trinidad?
Pauline está esperando para entrar. Dice que no le permite avanzar entrando en la reunión.
We have Jim, Howard.
And they are all getting in.
Yeah.
Yeah.
And I'm gonna make them co-host because otherwise they won't be able to
Great.
open their mics.
Good morning, Howard, Jim. Good midday, actually. Hi, Alex.
Wait, Alex can open his mic either. Now you can.
Hi, everyone.
I realized you did a change of look. You changed your looks, Alex. I realized that. Yeah, you.
Can you hear me okay? My wife cut my hair
We
because
can
it was
hear
getting
you
too hot.
perfectly, Howard. Your wife forced you, Alex. Very good.
Trinidad, I can see Pauline.
She says that she doesn't. She's unable to go any further. She's stopped when just.
Oh, now she's here.
Okay.
Now she's here again.
Yes.
Thank you.
Could I ask you a favor?
Yes.
Diana and Anna are going to be sharing their laptop. So I'm going to ask you to please put Diana as a participant and not as an interpreter so that they can use the different channels. Would that be
okay?
possible?
That would be the user of Diana Jasso as she's.
Yes, that's right. That's right. remove her as an interpreter.
Okay, perfect. And she's going to use the channel of Intert French.
Yes, that's right.
Okay.
That's right.
Done.
Okay,
Done.
thank you.
And
thank
I'm gonna add
So I'm going to take a couple of minutes just to introduce you all. Eduardo Toro, Luis da Costa, and Lukas Nellen are the three astronomers that researchers that are going to present today. Thank you very much for helping us. You are very kind. Then we have Howard, Jim, who just walk away, but he must be nearby, and Luis Cadenas. They are the directors of the Americas AmRENs. Luis is from RedCLARA, Howard from Internet 2, and Jim from CANARIE in Canada. Internet 2 is the United States of America. And then we have the team that worked for this is Tanya and Doyle, Catherine Antonison, and Alex Bushel. We are the amigos that we're working in this since a lot of time ago. And all the other names are the girls that are helping us with the translation. So thank you very much to everybody for being here today and helping us with your knowledge and patience and all the good things you do. And I hope we have a wonderful event today. I'm very nervous, I must say.
Only one. Sorry, guys. Thank you, Maria Jose. Yes, one clarification. I'm not an astronomer. I'm just information technology engineer.
Yes, I have it. I have that in the script. Sorry, Eduardo.
No, it is fine. Thank you.
Tanya, could you make sure that Pauline is there as an interpreter? Because she says that she's unable to speak. Maybe she's just as the unattendee.
It is just that I gotta make her co-host so she can speak in this general.
Hello,
now.
Tanya.
Hello, Pauline. Hi, good morning.
Let me
Good
speak.
afternoon.
Hi, how are you? Yes. Tanya, I just put INT at the beginning of my name. INT
Yes,
for interpreter.
yes.
So whenever possible, just assign me as an interpreter.
I think you are.
I'm going to join in with another device, which is Paulina. Don't use that as an interpreter. Use the one that has INT at the beginning.
Yeah.
Okay.
Now it should be ready.
No, I haven't received the invitation. Oh, yes, now it is. Okay, I'm accepting. Thank you. Well, all the best.
I'm gonna put it end. I mean, you won't probably see it anymore because I have you in the chart, but I'm gonna activate it just closer to the session. But you are now included, Pauline.
Okay, thank you. Tanya, I'm going to use a second device, which is called Paulina Disp DOS. And that is just as a participant.
Yes, I see it.
Good,
yes,
thank you.
It's okay. Thank you. And we have someone on the waiting room that is named C. Renan, but I'm gonna make them wait, or do we know that person?
No, not me.
We still have people registering now. So I'm trying to. We have 145 people.
Good number.
And well, we have now our link for the YouTube transmission. I'm gonna pin here the link.
And everybody's, I mean, all the Latin American immigrants are tweeting about this. Good, good, good.
Okay, these are going to be the blue minutes, just while we wait for people to join. While we start, I'm gonna share just for some minutes the information to give the welcome to the participants.
Perfect.
But I think it would be good also when they are here so we can see each other and everybody's faces.
Maria Jose?
Yes.
I think that person in the waiting room is a professor from Mexico based on the list that I have. It looks like it's Cesar Renan Acosta. He's a...
They are all getting in the room now.
Okay.
They are now entering. And we are live on YouTube.
So I think we have like 18 countries and 5 continents on this call.
Nice, no?
Participants won't be able to open their mics. We should invite them to leave their comments and questions through the chat box. Let's stop it just for a minute to activate our interpretation channels.
Tanya, you give the go, or I start at 1?
Just let me, you can start, please. I would suggest to give 2 minutes past the hour just to wait for the late participant, but just 2 minutes, and let me know just before you start talking to start the recording.
Okay.
And translation done.
Good morning to everybody that's connected. Nice to have you here. We will wait for a couple of more minutes in order to have more participants, and then we will start 2 minutes past 1. Thank you. Good day to all of you, and welcome to the first event of the Americas Research and Education Networks, bringing the universe to you. These days, due to the challenges that this pandemic has imposed us, it's more important than ever for national research and education networks to connect. The CEOs of CANARIE in Canada, Internet 2 in the United States of America, and RedCLARA in Latin America formed a common goal to work closely together and to highlight the research and education enabled by our network infrastructure and shared expertise across the Americas. With that goal in mind, a team of staff from all 3 organizations committed to regular meetings to explore what we do, who we support, and how we can better share our research and education network efforts. As a result, today we are launching the first in a 3 series of events that are open to the community, and we are very happy to have so many of you participating. Thank you for joining us. Today, we will learn how our infrastructures are supporting and enabling research in astronomy, and we will do it through the voice and experience of outstanding experts, namely Dr. Lukas Nellen from the Institute of Nuclear Sciences of the National Autonomous University of Mexico, Eduardo Toro Rivera, Information Technology Engineer at NSF's NOIRLab under AURA Observatories in Chile, and Luis da Costa, General Director of the Interinstitutional Laboratory of e-Astronomy, LINEA, in Brazil. The presentation of the experts will be followed by a few minutes for questions and answers, and then a fireside chat with our CEOs, Jinga Ban from CANARIE, Howard Pfeffer from Internet2, and Luis Eliezer Cadenas from RedCLARA. We invite you all to post your questions on the chat for the speakers in order to answer them at the end of their presentations. Okay, let's start. Without any further delay, I will leave this virtual stage to Dr. Lukas Nellen from the Institute of Nuclear Sciences of the National Autonomous University of Mexico. Lukas, the stage is yours.
Okay, thank you. Just okay. You should see my slides now. So
yes, perfect.
I'm very happy of this opportunity to tell all of you about both the exciting science we're doing, but also about how this all connects well and works only thanks to having access to the academic research networks of many continents and many countries. First, I want to talk about the PG Observatory as such. Is an observatory that is not what you normally think of when you're doing astronomy. Most astronomers work somewhere in the electromagnetic spectrum, which means here somewhere you have the visible part at the low energy radio and the cosmic microwave background. Here you go up to the very high energy photons in terms of gamma ray astronomy. What we are doing is actually studying charged particles, mostly protons and nuclei. There are a few electrons, positrons, and other particles at the very, very end of the spectrum. And if you see this spectrum is actually quite interesting, extent 28 orders of magnitude. At the highest energies, because they're hard to distinguish, we also count neutrinos and photons among the cosmic rays, even though in some classification they would be not counted as cosmic rays charged particles, but as neutral particles in other parts. So the cosmic ray spectrum itself spans 12 of the 28 orders of magnitude. What you see here in this plot, it comes basically as almost a straight line, which means we have a non-thermal power law spectrum. So it's not like a star that glows. It's some other mechanism that accelerates particles to these high energies. We know that up to about 10 to the 16, so here in this region, the galactic origin, we're pretty sure by now that above those energies, the extragalactic. So we're very clearly seeing charged particles, atomic nuclei, protons up to iron that are coming somewhere from outside our galaxy and reaching us at Earth. For the PG Observatory itself, the goal is to study the highest energy cosmic rays, which for us means above about 10 to the 18 electron volts. This is so here, this line. They're definitely extragalactic for all we can see by now. The flux is very low. At this high end, we're talking about 1 particle per square kilometer per century, or 1 per 1,000 square kilometers per year. So we're talking about the need to have very large instruments. Also, as a reference, here you see the 10 to the 18 mark. This is way above any terrestrial accelerator for particles and energy. So we have to understand, but we can also study particle physics, not only astrophysics at the very high energy scales. Like all these big instruments, you need a big collaboration. So in our case, the PG collaboration has almost 500 collaborators from 17 countries. For us here, it's very interesting. We have a lot of contribution from both South and North America. We have Argentina, Australia, Bolivia, Brazil, Colombia, Czech Republic, France, Germany, Italy, Mexico, Netherlands, Poland, Portugal, Romania, Slovenia, Spain, and the United States. The United Kingdom, unfortunately, for funding reasons, had to leave. It was one of the key countries in setting up this observatory more than 20 years ago. The observatory itself is located in Argentina. It's more or less, if you draw a straight line between Buenos Aires and Santiago de Compostela, and at Santiago de Chile. At the point where it crosses the Andes, you go a bit south, and then you see the observatory. I'm placing it here because of the concept of not on a geographical, but on the network map. Because what was very important for us is to have actually access to the fiber backbone of RedCLARA, which happened to cross from Chile to Argentina, not too far north from where the observatory is located. And this was a project that allowed us to get this fiber, which also provides connectivity to the city of Malaga, where we located. For me, this is an important message too, is that doing big science like this often allows us to help local communities, not just doing great science. And this is a great improvement. When we started, we had a few hundred megabits uplink by satellite. Then we had a microwave link, which was somewhat unstable. Having a stable fiber link to get to the data and to operate the observatory is very important when you're working in remote areas. And we have to work in remote areas here because of the type of science. We need a big area. As I mentioned, the flux is very low. The Auger Observatory itself, what's drawn out here, is about 3,000 square kilometers. The local reference I always have for here is it's about twice the size of Mexico City. So if you think of Mexico City as a giant city, this is twice the size. So it's pretty big. That's why you need access to the land. It also has an optical component, fluorescence detectors that oversee the site. We have 4 sites with 6 telescopes plus 3 extra elevated telescopes, a total of 27. And those can only work in low light conditions. So we have to be far away from cities. What we detect, the events we can see, in many cases, not only with one telescope and the surface detector part, but often with several of the telescopes to have stereo, triple, or even quadruple events. The observatory is also an important test bed for new technologies. Here we have a whole area, which is the AURA subdetector, where we're trying radio techniques as a new technique for radio detection, plus a couple for cosmic radio detection, plus a couple of places here which are for monitoring. For us, the air, the atmosphere is actually part of the detector compared to your typical particle physics detector, which would be where you control your media. We have to take what nature takes us in form of an air calorimeter of about 2.5 times 10 to the 10 tons. But since we can't control it, we have to monitor it. So I'm not going to talk a lot about it, but monitoring is always a very important part when you're out in nature. It's not just operating work. So the surface detector stations, you see them like here in front of the Andes in the Pampa Maria, consist of containers of 12 tons of water. So I'm saying this is not your typical observatory. We detect particles one by one. We have in there batteries to power them, electronic box, photomultipliers that detect the signals, solar panels to power communication antenna and GPS antenna. Important thing is this has to be wireless. You cannot cable 3,000 square kilometers. Copper is actually very expensive. So wireless communication is important. And those antenna that you see here as the communications antenna, they communicate with our fluorescence sites. You see here one of the communications tower, which has a microwave backbone link, and then cell phone derived technology to communicate with the individual tanks. This links to our main observatory site, and from there to the fiber and to RedCLARA ultimately. So here we have 6 telescopes in there, a LIDAR, which is part of the atmospheric monitoring. Inside each telescope, we have a filter and to correct the lens to have a big Schmidt type telescope, one of the simplest type of telescopes astronomers know, but sufficient for the quality of what we need. So, and it's at the same time a window to protect us from dust. Then a spherical mirror to reflect the light, and gets reflected onto a camera with 440 pixels, 440 photomultipliers. So how do we detect air showers? So what is that we actually detect? What we detect are air showers. which are particle cascades in the atmosphere. So you have the high energy particle, the high energy cosmic ray that hits the atmosphere from above and creates a cascade of secondary particles. And those particles do two things. They excite or ionize the atmospheric nitrogen, which creates near ultraviolet fluorescence light, which we see with the fluorescence telescopes from the side. And when the cascade, which forms like a slightly curved but almost flat plane that goes down, when that hits the ground, our particle detectors sample this shower front. And with that, you can see we measure this cascade in two ways. We measure the longitudinal development at clear nights only, and we measure the lateral expansion with a surface detector 24/7 continuously working. So how do we get information out of this? One thing first, to connect it with astronomy. So basically what we're doing is we take pictures of the sky, one particle, one photon. In astronomy would be one photon. For us, is a charged particles, one at a time, not like you do with a normal CCD. Then we have to synthesize an image out of these individual photons that we observe. So first, how do we get a direction? How do we know where that particle comes from? Well, this cascade, the shower front, hits the surface detector. And here, this is an image that's not from Auger, but much more visual. The timing is on this part. The detector gets hit first. You see the signal earlier, indicated by shorter lines, and later on the other part. And you can already see here, because this is something, a detector with many individual sub-detectors, you can see already the plane. If you remove the noise, you can have a very nice plane, which is exactly this shower front perpendicular to the arrival direction. So it's really geometry based on the fact that you can connect speed and direction if you know that everything moves at the speed of light. So another part, how do we detect, for example, the energy? That is a bit more complicated. The nice thing is that the fluorescence part is actually fairly colorimetric. So here you see, basically for the energy, you convert energy measurement and particle counting. You use the famous E equal mc squared of general relativity to say the energy of the primary particles. You convert in secondary particles. You know what's their mass, so you count them, and therefore counting the number, which is basically measuring that area under this curve, we know the energy. So this is how we have a calorimetric energy measurement. This, as I said, is the fluorescence detector that doesn't work all the time, works only about 10–15% of the time. But this allows us to calibrate the energy dependence of the lateral curves that we measure continuously with a surface detector by direct observation. So we do not depend on simulations. We really calibrate one detector with the other, which makes it a very robust measurement, which actually allowed us to detect that some of the modeling that we're doing in simulations is imperfect. We can use similar calibration techniques for other observables that I'm not going to go into all the details for reasons of time. Many other experiments that don't have this hybrid dual nature have to do Monte Carlo simulations to calibrate, and therefore have intrinsic larger errors. So with that, we combine the spectrum. We measure a spectrum of the particles. This is basically the end here, flattened out. You remember I had this graph which was steeply falling of the particle of the cosmic ray spectrum. We multiplied here with the fact that basically flattened it out so you can see this, the structure here. What you see is at the very high energy, the particle flux all of a sudden really cuts off, which could be a cutoff in the propagation, that the universe becomes opaque for high energy particles, or that the sources that we have simply don't have the energy to create particles with energy. This is still an open question to be addressed, and it's part of the research we're actively doing. Another part of the research is asking ourselves, where do those particles come from? Charged particles compared to photons have the problem that all the magnetic fields that the galaxy, everything in the universe has, sends them down in spirals. And therefore, they lose the information of the original source. It's not like a nice photon. When you see light coming from the sun, you know there is the sun. When you see it from a star, you know there's the star. Here, seeing the particle coming from there doesn't mean the source is there. The source could be anywhere because the magnetic field moved it around. At very high energies, though, these deflections become small enough that you start seeing a correlation between what you see on the sky and where the particles come from. So first indication that we have here at the high energies is just a dipole, that we see more particles from one region here in this region. This was actually an important result, which was listed as a 2017 top 10 breakthrough. We see this here. This maximum is displaced from a high overdensity in matter, which is where we would expect galaxies to accelerate particles. And the displacement is more or less consistent with what we would expect from a displacement by magnetic fields in the galaxy. So this paints a nice consistent picture, but we still don't see like a single source coming up. This connects to something we ask ourselves, what is it actually? I've told you what we're seeing is from proton to heavier nuclei. Which nuclei do we actually see? This is not so easy to tell, but we have some hints. And for this, we have to think about how do the cascades form? Well, a proton is obviously smaller than an iron nuclei. In technical terms, this would mean the cross-section is smaller, but this means the proton is less likely to interact than an iron. A big ball is more likely to hit an obstacle than a small ball, basically. So, and this has a consequence that a proton can take longer, can travel for longer in the atmosphere than an iron nuclei. You see this when you simulate them. Protons, in general, on the average, have air showers, air cascades that develop deeper than iron. They also fluctuate more for the same reason. So we have two parameters that we can measure: the depth of the maximum, where the maximum of this curve is, and the fluctuations of this, that give us an idea of what's the mass composition of what we're seeing. And when we look at this, we see here, we can really compare this to simulations as a function of the energy. Graphed here is the depth of the maximum, how deep where that maximum of the curve occurs in the atmosphere. And you can see, compare this with simulations here by different codes. That's why there are several lines. The proton line at the top, the iron line at the bottom. And you can see here that what we observe indicates strongly that we see lighter nuclear protons predominantly at lower energies, heavier nuclei at larger energies. And you can see this also in this other, in the fluctuation parameter, where here you see on top of it points outside the allowed band, which is what I mentioned before. We have indications that some of the models that go into simulations are not realistic, and we return this as a challenge to the particle physics colleagues are saying, you have to work on those models, something there is wrong. But what we see also as a problem is if the high energy nuclei are heavier, they bend more than protons, so we have a harder time identifying sources. So we hope to improve that. I have a slide on this later on. Something else which I thought was very exciting, this is why I added here. You all remember the famous gravitational wave event from the 17th of August 27, which was a neutron-neutron star merger. We don't have many of those. Most of them are black hole mergers, but this was what we also know as a short gamma ray burst, which has been confirmed by the Fermi and the integral instruments. So, and you see this here, the gravitational wave chirp, you see the Fermi LAT gamma ray burst signal, which was essential, that started really a big flurry of multi-messenger observations. And we were very lucky. Auger, together with IceCube and Antares, can work as a neutrino detector. And we were trying to see if there are any neutrinos at high energies that came from that region. The message is no, there weren't any, which means some of the theoretical models are already excluded. It is not something, a great surprise. This was not one of the highest energy events, but for us, and this is, I think, something which I want to give, we were very lucky. That event, which is located on the sky here in this zone, fell right in the area of where Auger has the maximum sensitivity. So we could establish some of the strongest limit and therefore push back theoretical modeling of those sources quite a bit and tell them these kind of models don't work. We have active programs running follow-up of all these kind of sources and collaborate on this kind of multi-messenger astronomy in many other cases. Now, what we're doing is we're working on an upgrade. As I mentioned, it's difficult to do details of the composition, whether we have protons or iron or heavier nuclei, and this makes it difficult to do astronomy with charged particles. So if we have a detector that can better separate information of the secondary particles in the cascade, it can give us more information, even event by event, on the primary cosmic rays to determine, for example, I mentioned the spectrum, the flux suppression at the end. The question, is this what we call the GCK cutoff, which is basically protons of nuclei no longer being able to transmit, to propagate freely in the universe because they collide with microwave photons and get stopped. The universe is simply not a perfect vacuum. Or if it is that the sources can't accelerate to higher energies, and we're seeing an astronomical effect, not a propagation effect. So we want to, and for the astronomy, we want to see or enhance our proton component. And we want to be able to study more details of the air showers at the highest energies. As I said, this is above LHC energy. So we also, in that sense, not just doing astronomy, we're also contributing to particle physics with our observatory. Here's a picture of how an upgraded detector station will look like. The one in front is one of the earlier test stations for radio. Here at the back, you see the stations as we expect to have them. A scintillator counter at the top, which looks like a corrugated roof mounted on this, actually has a small detector component added. We're updating the electronics to have new, faster electronics to get more signal out of it. We're adding a radio antenna, which is especially useful for horizontal air showers and the electromagnetic component. So all this is funded and is being set up. We have prototype in the field for that. Something else which I think important for everybody, not just for us, as many other experiments, we're working on open data, releasing part of our data to the public. We've done it for the first time really in a systematic way this February. You can get at these links, opendataauger.org, or at the Mexican Mirror, you can look at them. These are data sets that come together with Python notebooks for people to look at Auger data. We have basic analysis in there for people to look at how we're doing our papers. And these are real analyses that come from, that are almost full versions of the analysis we have published. This data release is more aimed at scientists. We are now working on a release for the general public, which is for outreach purposes to be used in master classes, and something which we expect to have ready in another 2 or 3 months maximum, probably somewhere in the summer. Something else which is important, which is not directly science, but very important for us, is that we have remote control rooms that can only operate because we have good network connectivity to the site to operate the observatory. This is the observatory control room at the bottom. This is the control room we have in Mexico. You see up 6 screens for the monitoring, and at the bottom 2 pairs of 2 for the operating of the telescopes. You see here the green indicates that this is a real life picture from when we were actually in operation, not a staged picture from testing. And here you see another one of the control rooms that we have. There's 16 now worldwide, also in different time zones. So you can use the fact that North America is on one side, time zone wise of Argentina, Europe is on the other side. You can start in North America early in the night, and then at midnight you hand over to Europe, which will be 7 in the morning for Europeans. It works perfect to share the load of operating. It reduces travel costs. It also reduces CO2 emissions working from remotely. And it's been proven essential now in the COVID pandemic time where we couldn't travel and do in-person shifts at the site. There are many more results than what I could present here in a short time. I've shown you a little bit of the spectrum, the angle suppression and the anisotropy. We have many more limits on neutrinos and photon limits, which rule out many theoretical models. We've looked for exotic particles like magnetic monopoles, which are predicted in cosmology, Lorentz violation of basic relativity symmetries. We have looked at, we have observed discrepancies with some particle interactions. We've done, as I said, the neutrino follow-up for LIGO gravitational wave events. We've measured high energy proton air cross sections beyond the reach of terrestrial accelerators. There's some beautiful non-cosmic ray science that we're doing related to atmospheric science, lightning observations, and so on. So there's many more things. I really invite you to look at the site or attend one of our bigger colloquia that colleagues give all over the world. The upgrade is in progress to extend the science reach, an instrument that is now almost 20 years old. At some point, just running it for longer doesn't buy you more science. Something else that is important, this experiment also had led several spin-off or related experiments. For example, in Mexico, we have a strong participation in the HAWC Observatory, where we actually, the primary data center and move the data are, again, important from the point of view of us for these experiments. The strong network component, we're working with LHC, ALICE is strong in my institute, there are also CMS groups. Because of all this success we had, we got approached and started to get contact with the wider astronomy cosmology context. We have collaborators in the DESI and LST surveys, which are now sharing our data center. And all this has been also a driver for the HPC infrastructure in general in Mexico in our case. And we've learned and we've developed technology or imported technology to run big data sets. At the moment, we have 7 petabytes about in the institute, which for Mexico is a large scientific data set. And we've pushed forward the networking in the university. By now, we actually managed to move from about 60 megabits we had when I started to now 10 gigabits between our data center and the US. So here I leave you with a few more pictures and the links, the first one in English, the second one in Spanish for the PG Observatory. So thank you.
Thank you very much, Lukas, for such an interesting presentation. There are a couple of questions for you in the side chat, if you could answer. But please stay connected for the question and answers load after your colleagues' presentations. Now it's time to invite Eduardo Toro Rivera, Information Technology Engineer at NSF's NOIRLab and the AURA Observatories in Chile, to share his presentation with us. Welcome, Eduardo, and thank you very much.
Thank you, Maria Jose. Hello to everyone, wherever you are. I will share my screen in order to show the presentation. Well, how Maria Jose said, and after the very amazing presentation from Lukas, the dimension of this presentation is going to the information technology. As information technology engineer, I'm working in the NOIRLab, which is the National Optical Infrared Astronomy Research Laboratory for the United States that depends from the National Science Foundation. So the agenda for this presentation is basically a general overview of the Gemini Observatory, because we will focus on Gemini Observatory since this program is one of the NOIRLab programs that contains the facilities, telescope in Chile and Hawaii, and we have United States and Canada as part of this member of this observatory. We will talk about the IT Ops, about this group that develop and implement, design the information technology operation service, which is IT Ops. We will talk about also the backbone networks that is really important for us overall in this new era of the astronomy that is basically being moved by Vera Rubin telescope in Chile. We will talk about the initiatives that we have, the integration between Gemini South and medium scale observatories, which include the legacy observatories in Chile, like Cerro de Lolo. Also, we will talk about the last activities and networks during the 2020 and the pandemic era. And also we will talk about the future network activities. Okay. Before to talk about the Gemini Observatory mission and NOIRLab mission, I would like to share with you a beautiful video about the activities of Gemini and science and the community's outreach. Okay, as you can see in that video is a brief summary about the scientific functions from Gemini Observatory, but also the relation with the community. That was an amazing local musicians, young students in La Serena that did that presentation under the dome of Gemini South Telescope. But let's return to Gemini Observatory in terms of the missions. The mission currently from Gemini Observatory is advancing the knowledge of the universe by providing to the international community, Gemini community, with front access to the entire sky. However, now since Gemini Observatory is part of the NOIRLab, this big institution now, the mission is expanding to another elements of the mission of the NOIRLab. It's basically enable the breakthrough discoveries in astrophysics, developing and operating state-of-the-art ground-based observatories. And here's the key: providing data, products, and services for a diverse and inclusive community. That is the key new roles of Gemini in terms to growing in this new scenario. But what are the NOIRLab programs that Gemini Observatory is working together? Is working with the Cerro de Lolo Inter-American Observatory, with the Community Science and Data Center, absolutely involved with the Kitt Peak National Observatory, and also in the era of the NOIRLab, or the era of the Vera Rubin, the big data. Vera Rubin is part of the NOIRLab, but right now it's under construction, is very close to the Gemini South in Chile. So that's implied that we are sharing part of the infrastructure that we will talk about in a few minutes. Okay, so to understand the context of the Gemini in the hemisphere south and hemisphere north, we will understand that Gemini South is in Chile in the Elqui Valley at 8-meter telescope, and also in Mauna Kea, Hawaii. And we are part of the, who I mentioned before, the NSF NOIRLab with ground-based telescopes. but also we are being administered by AURA Corporation. So AURA Corporation has another responsibilities, not only the ground base. They have the Space Telescope Science Institute and also the National Solar Observatory. And that groups of institutions we have, for example, the Space Telescope, Hubble, James Webb Space, Mass Data Archive, the Nancy Grace Roman, to mention some of them. So this is the scenario of the International Gemini Observatory, that we share some kind of the scientific challenges with the coordination under the umbrella of AURA to the administration, but under the NOIRLab to the ground-based telescope. Well, return to Gemini Observatory then. What is the motto of Gemini Observatory? It's one observatory with two telescopes. Who I mentioned before, we have telescope in Gemini North, Mauna Kea Mountain, and also in Gemini South in Cerro Pachón, Chile, in the Elqui Valley. The current Gemini partners are United States, which is the leading of the percentage of the community of Gemini Observatory. We have Canada, Chile, Brazil, Argentina, and South Korea. In the previous video, I didn't mention South Korea because South Korea arrived to its formal partner of Gemini and just 2 years ago only. So in the bottom of this slide, you have here the institutions that it's part of the being administering for each country. The National Research Council from Canada, the Ministerio de Ciencia y Tecnología de Chile, Ministerio de Ciencia y Tecnología e Innovación Argentina, KACI, which is basically the Korean Astronomy Space Science Institute, and also the Ministerio de Ciencia y Tecnología de Brasil. Okay, that are the institutions that are behind of these telescopes or observatories. Okay, let's talk about the Information Technology Operations Service. It's basically the department that have the missions to standardize all the infrastructure, IT infrastructure, and also the system deployment and manage as well as the IT support requirements, reaching all the levels of NOIRLab. In that terms, we have, or we need to include the IT operations and the business IT operations, because there are two key elements of the information technology in the observatory. The business IT operations basically delivers and supports all the integrated IT services across all NOIRLab sites. And we provide the IT service necessary to run the business and this new modern corporation. And also we have the astronomy IT operations, because it's basically we need to be clear that the telescope needs another kind of technology in terms of the communications, control systems, the instrumentations, and obviously that is very important to the functionality of the telescope. So the astronomy IT operations delivers and supports that enterprise computing services. To provide that kind of services, we have a team of 23 people working in Chile and Hawaii, and also in Tucson. But in Gemini Observatory, right now we have a team in Hawaii and a team in Chile that it's part of the NOIRLab too. So a little confused because I have a lot of institutions involved in this big institution. Okay, going more deeper in the relation with information technology, we need to talk about the data centers. The data centers that we have in Gemini Observatory are 4. 2 of them are in Chile. One is in La Serena Base Facility. Another is in the telescope in Cerro Pachón. Another 2 data centers are in Gemini North, in Hilo Base Facilities, the city of Hilo, and Mauna Kea Mountain. So in that data centers, we concentrate many of the efforts to provide the connectivity and the functionality of all the network services that we provide to the telescope. What are the key use cases that we need to consider in this function of telescopes? The first one, to Gemini point of view, is the base facilities operations, which is the remote observing. Even like Lukas mentioned in his presentation, they have also a remote observing. But this is a remote observing from an 8-meter telescope, a little more bigger. So the consideration technicals could be more complex. We have also VPN access. We need to provide virtual private connectivity to the external and remote users. Another element that we have considering in these important activities of IT is the connectivity between the base and the summit. In this case, from La Serena to Cerro Pachón, we have or we need a high bandwidth to the current instruments that we are working in the telescope. The high availability in a world-class observatory should be more than 99%. That means that we need to be available, all the system, 99% at least during the year. The high availability is also an important element because we are upgrading all the data center in the range of 10 years. So that is the maximum MTBF, that it's basically the mean time before failure. So each 10 years, or even with 8 years, we are replacing everything in the telescope. Another key element is the cross-site coordination, where we have a low latency between La Serena and Hilo, or La Serena and Tucson, depends on the functionality that we are checking. And finally, another key element is the cloud data archiving. Currently, Gemini Observatory is put their data in the Amazon Web Services. That is currently the storage external that Gemini has. For that, we need to stable internet access to reach that service. So let's go in deep again about the data center. Who I mentioned before, we have base facilities operations with remote observing. You can see in this picture 2 observers that have all the control from the different metrics that are necessary to check on the mountain, not only the weather, not only the instrumentation, the sky, is basically all the remote access to the all infrastructure on the telescope. So with 2 persons there, it's possible to control everything and monitoring everything. Even if somebody is from the United States or even from Korea, we have done some observations, it's possible to have control to a specific instrument with very secure access using an important or some specific VPN applications to do that. In terms of the instrumentation, the telescope offers many of them. I don't want to be here a class about the instrumentation. There are a lot of them. You can check in the gemini.edu webpage that I mentioned here in this slide about what that's mean, all these acronyms, GMIS, GSOI, GPI, Flamingo, GEMS, etc., etc. But the only thing that I could say, it's they have many functionalities in terms of the planetary system, about the spectrometry, imagers, etc., etc. So for now, we are working in instruments that need or require more data transfer. Even also the visiting instruments that are basically present in Gemini, they are sometimes working on Gemini, and even they have access externally from remote users. About the data centers, key use case, another element is the high bandwidth. Currently, we have 4 fibers of 10 gigabit each one to reach the mountain from La Serena to Cerro Pachón. I'm talking about just from Gemini South. And we have another microwave link of 300 megabit by seconds that's permit to have a backup in case of the fiber failure. All this is automated and easy to work and very transparent to the observers during the night. Important for us is to understand that we have redundancy from La Serena city to Santiago through different circuits provided by Reuna and Telefónica, and that for us it's provide a consistency and a high availability to not only to send the data, it's also to have external people from everywhere that it's need to access to the telescope or some resources in the observatory. So the same idea, it's going to United States to reach internet too, or commodity internet. We have two links in terms of the primary and secondary. We could say that for us, Gemini Observatory has worked very well in terms that we provide accessibility to many external communities that are working with Gemini, and not only for different countries, it's only to instrument visitors and many others investigators that they need to access the services that Gemini provide. Okay. Talking about the high availability, high redundancy, during the last year, I don't know to say and explain all these high-level diagram in details, but for your knowledge, the more important thing is that many elements in these diagrams is redundant. We have redundant firewalls to the external connectivity. We have redundant cord just to protect the internal networks. We have redundant access just to maintain the high redundancy, whatever. That is the philosophy of the construction of the data center. At the same time, we have redundant access in terms of the uplinks to the base and the mountain. The right hand is the mountain, the left hand is the base, in the case of La Serena and Cerro Pachón in Gemini South. And also, we are working high in terms to provide new network services. We have very concerned about the instruction prevention systems, about the anti-malware protection, URL filtering, all the activities that is related with the IT, with the new equipment. We did an upgrade, but again, this infrastructure has at today 7 and 8 years old. So we are very close to replace many of them. So that is as part of the advance and the changes inside of the Gemini Observatory. What is the cross-site coordination between the different locations that are part of the NOIRLab? We have VPN site-to-site between La Serena and Hawaii. What is a VPN site-to-site? It's basically that we are connecting directly to our network services in Hawaii and vice versa, using encryption and absolutely accessible for every investigator that is in each part of the hemisphere, north or south. So every user from Gemini North can reach all the services in Gemini South. That is, it's the idea of this VPN site-to-site. The same idea we have with the connectivity from Gemini South to Tucson and Cerro Tololo to Gemini North, etc., etc. We have the connectivity, and for us, it's a key element to do the cross-site coordination. Since we have many time zones different, we have 6 or 7 hours of difference with Hawaii, it's very important to us to have all these kind of services up and running all the time. Well, during the 2020, basically, we start integrating Gemini Observatory in the south with Cerro Tololo Inter-American Observatory in Chile. That permit us to increase the capacity of the observatory and also provide new network services to the different group of the scientific. And also we share different tools, instruments, but in general, the infrastructure to work. We are in La Serena, an amazing buildings that concentrate the functionalities of Gemini, Cerro Tololo, and now very close, Vera Rubin Observatory with one of the last state-of-the-art data centers that we have in La Serena. Okay, so many activities related with the networking in terms of the wire and in terms of the Wi-Fi, VoIP system, VPN, etc., etc. That we started during 2020, But also we create the conditions, the new connectivity to pass directly connections between Gemini and Cerro Tololo. Now we are creating a unique infrastructure to share all services. What were the Gemini South improvement during 2020? It's one of the important elements is the next generation firewalls. We are offering to the external users the latest in technology in terms of the connectivity through that firewalls. This is the only probably device that we don't need to change in the next couple of years, but we'll change the rest of the network. But that provides us important challenges in terms of the information technology. Also, we need to advance in the authentication and authorization to many users and that share the network services from Gemini and in other countries. So we're still working on it. We still we need to do a lot of work, a lot of activities to continue with the integration between Gemini and medium scale observatory. What will be the future activities? It's basically the same, but it's now we are working in Cerro Tololo. I don't want to talk more in detail about that, but it's the big challenge here is to maintain and update all the infrastructure, standardize it. So the standardization is basically our bigger problem right now. And we will take at least 3 years to upgrade all the network in La Serena, in Hawaii, and also in Tucson. So we are going in that direction. Another element that will be very interesting, that we will start it for now, and when Vera Rubin Observatory start the operation, because now it's under construction, and a very close collaborative and integration with all the information technology that Vera Rubin provides. Vera Rubin has a very interesting element that is just for another presentation, but it's a challenge also to Gemini Observatory to take advantage of some experience of Vera Rubin Observatory. The more important project that is coming during the next year or 2 or 3 years more is that I mentioned before. It's just to upgrade the network, exchange to everything. We are starting the kickoff meeting for that project. That will change everything. We will change all the elements that I mentioned in this presentation, but it's most important is to keep in mind that all the requirements are practically the same, and probably one of that requirement will increase in terms of data transfer and access to the archives or any other element related with that. It's basically that where the instrumentation is taking more resources from the organization. And here appear some preliminary LAN design, local area network designs, in order to understand what will be the model of functionality to the future. We will still maintain using the similar links to internet, commodity internet, internet 2, but also we will have any other elements in terms of the technology and speed, latency, etc., etc. So that is the presentation from Gemini Observatory. I hope you enjoy and knows a little more about the International Gemini Observatory. Thank you.
Thank you, Eduardo. We certainly enjoyed your presentation, and I'm extremely thankful with you for sharing with us the wonders of Gemini. That personally, I would like to have more information in the news, at least in Chile, in our country, about this wonderful initiative. Please stay connected, and I invite you to watch out the chat in order to answer a few questions. I have already seen Lukas answered all his questions, which I'm very grateful for. And now it is time to present Dr. Luis da Costa, General Director of the Interinstitutional Laboratory of e-Astronomy, LIneA, in Brazil. And Luis, the stage is yours. Please go ahead.
Okay, thank you, Maria Jose. And I can see that we are running a bit late in time, but I'll try my best to catch up. Well, today I would like to highlight the contribution, the incredible contribution actually, that the networks are providing to the work we are carrying out in recent years in the exploration of the universe. Let me start by saying that the progress in cosmology has relied entirely on the progress of technology. In fact, modern cosmology started only in the late 1970s with the appearance of the solid-state detectors. Only then was it possible for us to probe a volume of space that was large enough that would be relevant for our understanding of the universe. So basically, in the 80s, there was a flurry of surveys, some of which I'm showing here. Here on the left was one of the very first surveys of analyzing the distribution of galaxies. Each point that you see here is supposed to be a galaxy. This is the distance of the galaxy towards us, and these are slices that are across the globe. So this was a combination of an effort led by the Center for Astrophysics and us in Brazil carrying out the Southern Sky Redshift survey. So this was the Northern Hemisphere, this was the Southern Hemisphere. And the point is, was the first generation of very large astronomical surveys, with the understanding that the large were actually quite small by today's standards. Here it was a very tough work. We were able to observe 10,000 galaxies in the period of 10 years. And the total cost was about $100,000. And the international collaboration was basically 2 or 3 institutes. And the total number of researchers was about a dozen. The same thing in the late 80s, starting in the 90s, was done with another collaboration between Cornell, Dartmouth University, and us in Brazil too, that was to study the distribution of the peculiar velocity field of galaxies, even from that be able to derive how the mass, not only the galaxies, which is the luminous part of the matter, but the dark matter was distributed in the universe. So the blue points basically show galaxies that are moving towards us, the red points.
Luis, I'm sorry to interrupt,
sure.
but you are not sharing your screen.
You are not what?
You're not sharing your screen. You are not seeing your presentation.
Oh, just a second.
I'm so sorry to interrupt you. I'm gonna take advantage of this seconds in order to.
Oh, I forgot. I forgot to click the button.
Yeah. So I'm gonna take advantage of this problem just to tell the audience that we are not gonna have questions and answers after the presentation of Luis due to the time constraints. So go ahead, Luis. I'm sorry for interrupting.
No, it's fine. I apologize for the mishap.
Don't you worry.
Anyway, so here are the galaxies, like I was trying to mention. This is a slice of the universe. So basically, this is distribution space of the galaxies, and this was meant to be to explain the peculiar velocity field of galaxies, how the galaxies move in response to the gravity field that is generated around them. So basically what we see here is just the luminous part, luminous galaxies, but here we could actually probe the underlying mass distribution, not just the galaxies. But the point there was that this was the type of surveys that were made possible with the development of new technology. So just from those results was already pretty obvious that we had a wrong picture of the universe. We thought originally that was dominated by cold dark matter, but these very first results already showed that there was something wrong with this picture. And this was kind of confirmed in the late 90s by studying the expansion history of the universe. So that was not how the clustering of the galaxies would work, but rather actually measuring the expansion of the universe by using the explosion of supernovas, which are sort of a standard candle. That is, we know the intrinsic luminosity of these objects, and therefore we can estimate the distance. And what these people found, this group found that there were 2 groups. What they found was that the supernovas were actually more distance than we expected, which actually was interpreted that the fact that the universe was actually in expansion. This discovery was extremely important in terms of the underlying physics. It meant that instead of contracting, you would expect that the universe would contract in response to the gravity, actually was expanding, accelerating its expansion. And the only way to do that was that the need of a force that would counterbalance the action of the gravity. So this led to a situation where the universe, as we know, it's composed by ordinary matter of about 5%, dark matter, which we don't know what it is, and this new component that was named dark energy that would correspond to almost 70% of the composition of the universe. So what this meant is that there was something else, a force in the universe that nobody knew its origin. Nobody still knows its origin. And so this would mean that it will require some new physics to explain its nature. So after 40 years of investigation, so we got to a conundrum where basically that our understanding of the cosmological model, the current cosmological model, relies in three pillars, out of which one is dark matter, dark energy, and inflation. And we don't know anything about them. So that's the situation that we face today. And it is the motivation of the work being carried out today. It actually can be divided in three different areas. Inflation, I think, is the domain of studies of the cosmic microwave background. Dark matter, as you all know, is the Large Hadron Collider, LHC. And the dark energy is actually exploited by astronomy. So back in 2005, the Department of Energy decided to convene a committee of pundits to discuss what should be done in terms to get better constraints about this so-called dark energy. And there was a list of several projects, several large surveys, some of them spectroscopic, others imaging surveys, and they divided in two different stages, stage 3 and stage 4, depending on the volume that they would explore of the universe. So basically, we are in the phase of stage 3. So there are several projects: Sloan Digital Sky Survey with this EBOS component, the Dark Energy Survey, and there are two others, both imaging and spectroscopic. But the interesting thing that this new generation of surveys were, first of all, large multi-year surveys, given the scope of the surveys. They all involve international collaborations. But instead of that limited number of countries, 2 countries, 10 institutes at most, we are talking about thousands of collaborators, basically 20, 25 countries, a large number of scientists, dedicated telescope time, large volumes of data. It actually can be used for different applications, and actually these are major projects involving millions of dollars. And there is the stage 4, DESI, Euclid, LSST, which is now called Vera Rubin telescope. It also WFIRST, that's now called Roman telescope, is a space satellite. Brazil decided to participate in this, and basically we joined in these different projects, the total 4 projects at different years. We joined DS in 2007, 2008 we joined Sloan, 2016 we joined DESI, and in 2015 we joined the LSST. And the way we joined them was a sort of a consortium of scientists, and the membership was always negotiated in sort of a combination of in-kind or combination of in-kind and cash, mostly in-kind contributions. And this was actually the reason to create LINEA. LINEA is actually who negotiates these various agreements. The ongoing projects that are the Dark Energy Survey and the Sloan Digital Sky Survey, both of them have their observations completed, and they are in the period of analysis. And now we move on to the next generation, DESI, which is just starting the observations. It's called the Dark Energy Spectroscopic Instrument. And the key numbers are that they're going to observe, it's a 5-year project. They will observe 5,000 objects. And this, the spectra of the object will be split in 3 domains. Therefore, each observation will involve 15,000 spectra. They are usually 10 minutes exposures, and they will observe 35 million objects in 5 years. Just to give you an idea, we observe, like I said in the beginning, about 10,000 objects in 10 years. They observe 10,000 objects in less than 1 hour. So this is to give you the degree things have evolved over the past 40 years. But the big project that is coming up is the LSST, the Legacy Survey of Space and Time, which will be carried out in the Vera Rubin Observatory. The incredible thing about that is the numbers, the key numbers of this project. It will be 10 years of observations. We'll observe half of the sky in 6 filters. Each image is about 6.5 gigabytes. The camera itself, I mean, can you imagine having 40 full moons in the sky? That's the size of the field of view of this camera. One image is taken every 15 seconds, and will generate 15 to 20 terabytes of data per night. And the image must be transferred from Chile, from La Serena, all the way to SLAC, which will be the US data facility, in less 20 seconds. So that's where the networks come in. This data has to move very fast, because that's meant to be reduced in less than 1 minute to be able to trigger events of any alerts, objects that change the brightness or move, moving objects of the solar system. This will actually generate about 10 million alerts per night. And each position of the sky will be visited 800 times. So we're actually going to produce a little movie of the dynamical universe covering its time span of 10 years. It's an unprecedented project. It will allow a census, full census of the solar system. We'll generate catalogs with about 40 billion objects. There will be yearly data release for the collaboration for those that have the data rights, and public data releases every 2 years. So this is something that will modify the panorama of the astronomical community in the next few years. So that was the reason of creating LIneA, by the way, because we needed something, some organization that would provide the infrastructure, computational infrastructure, the in-kind contributions, and the logistics of the working collaboration in Brazil to provide support to these big science projects. And LIneA was created officially in 2010, but actually we started way back in 2007 when we joined the Dark Energy Survey. So we have our own dedicated infrastructure, which is located close to this Brazilian supercomputer in Petrópolis, which is a city about 60 kilometers from Rio de Janeiro. We have our own dedicated machines. We have our system for optimized for data transfer. We have a storage, which right now is 1.5 petabytes, and we have about 25 teraflops. But we also have access to the supercomputer. We have about 2 million CPU hours in the supercomputer. We also provide services. I mean, we have a mirror site of the Sloan Digital Sky Survey here in Brazil with about 20 terabytes. This is actually, we maintained that for the past 10 years. And we are now also serving the data from the Dark Energy Survey, which consists of 6 years of observation. This is going to be made available here in Brazil and also at NCSA where we have also one of our interfaces. We also will provide several science platforms for the Brazilian astronomical community involving the Jupiter Lab, HPC, access to HPC. We have something called Science Server to actually visualize images and catalogs from the Dark Energy Survey. We have a science portal, which I'll briefly mention what it does. We have a portal also for estimating for the applications of the solar system, and also have something called Manga Portal to visualize the cubes, data cubes that are produced by the Manga survey of this long digital sky survey. So we actually develop software, specialized software, to help our users to actually analyze and visualize the data they are processing. These are the science platforms. Like I said, we developed one to make predictions of occultations by objects of the solar system. This was done for this Trans-Neptunian Occultation Network, which is a French-Brazilian collaboration. We have developed this Manga Portal for this long digital sky survey, and we have developed several tools for the dark energy survey. One which has been used during the 6 years of observations at CTIO to actually assess the quality of the image being taken by the dark energy camera. And we also did this for to access the data, the reduced data. This one was actually available at the NCSA. And we have the Dark Energy Survey Science Portal, which basically is an infrastructure to host all kinds of pipelines so that we can analyze end-to-end the data that's arriving. So we start from objects detected in the images all the way to cosmology. So this was a very ambitious project. So right now we give support, particularly for scientists that are directly involved in these several scientific collaborations, but we are in the process of actually making these services also available for the community in general. And for that, we have been working with RNP to actually to integrate the LIneA in some kind of identity provider using this federated cafe, which allows for login by people. It's basically an authentication authorization system, so that we can provide service for different profiles of users, and also to developing, again, with the help of RNP, Kubernetes clusters to actually be able to provide the service in a sustainable way, making sure that we have enough cores, enough memory for all the users. But what really is changing us in our goals is LSST. So we were able to join LSST as a partner. We have an MOU with LSST since 2015, thanks to the RNP and ANSP, because of Brazil became responsible for the connection between Santiago and Boca Raton. And with that, we managed to get 10 PIs in the project, 50 scientists, Brazilian scientists. But more recently, we also applied another in-kind contribution. We are still negotiating with the LSST, but basically we hope to host a data access center, a so-called independent data access center here in Brazil. So this is the picture that Jeff Cantor sent to me, basically showing the contribution that Brazil is providing, which I believe comes from Santiago, São Paulo, Boca Raton, which is actually the primary path, but there are a lot of redundancies in secondary paths to get the data from Cerro Pachón all the way to US Data Facility, which now has been assigned to SLAC in California, in Palo Alto. And the idea now, since the data will come from La Serena, go to Santiago, pass through Brazil, go all the way to US Data Facility, what we intend to do is to be here and create this IDAC, as they call. So this is a very important thing for us, because there are many benefits from having this IDAC. First of all, it provides us with more data rights for the Brazilian community. We hope to increase from 50 to more than 100 Brazilians users with data rights. It provides us with efficient data access to the data, allows us to have the data close to our HPC infrastructure, enables us to reuse the tools that we developed for the dark energy survey, which was basically a precursor survey of the LSST. We will have the support of a specialized local team, and encourages also investment in a data center and eScience Institute not only for astronomy, but hopefully we can aggregate more different groups to help us out and make sure that we have a more robust infrastructure. What are requirements to have this IDAC? It means that we're going to have to be able to support a database of about 500 terabytes, and we intend to develop a system called the Q-Server Distributed Database, 5 petabytes of storage, 500 cores, 40 gigabits per second connection sustainable. We will probably require 5 FTEs to operate this IDAC, and we have to support 50 simultaneous users wherever they are. Anybody with data rights will be able to access our system. And we have to cover about 9 different time zones. As a final remarks, let me just say that the networks have been extremely important to contribute to enhance these international collaborations. I've been collaborating over 40 years internationally, and the change is remarkable. I mean, we really feel like we are just in the States rather than having to deal with the emails and I'm from the time that we had Telegram, so it's a long time ago. So the benefits are incredible. Network is critical to implement this IDAC and all the benefits it brings to us. The networks are literally bringing the universe to the IDACs. I mean, is to bring the data, which is the sky, for 10 years. It will be available on our disks or in the cloud, but accessible, register in some media. And we are still carrying out some end-to-end tests, including the national connections. We always have these last mile problems, and we are still figuring out how to improve the connection between Rio and Petropolis. And the requirements that we have are we both need bulk international transfers, but also national international accesses, for, like I said before, from 9 different time zones. So I just like to say that without the networks, this certainly will not be possible. So exploring the universe, it does need now today this new technology, and hopefully much more than 100 gigabits per second. Thank you.
Thank you very much, Luis. And it is a very happy thing to know that we are working. I mean, when I say we, I say Internet 2, CANARIE, and RedCLARA. We are working for support this kind of research so relevant for humanity. So I feel proud to be part of this in a very, very tiny portion. We sincerely thank the great contribution and collaboration of you, Luis, of Lucas, and of Eduardo, and please count with us in order to share your research, and we will be more than happy to help to disseminate your efforts within the entire continent and hopefully with the rest of the world.
Thank you.
Because of time constraints, we need to carry on.
Move on.
Thank you. So networks in the Americas are led by the CEOs of CANARIE in Canada, Jim Gaban, Internet 2 in the United States of America, and Luis Eliezer Cadenas from RedCLARA that interconnects all the AmRENs in Latin America. Let's start with the question, gentlemen. So I'm going to send the first question, and I think Jim is going to catch this up. These research and education networks are super different in so many ways. How do you leverage the trends of each organization to support research and education communities across the Americas?
It's a great question, Maria Jose. First, hola, bonjour, and hi to everyone. It's naturally a human thing to study differences and try to understand differences, and we definitely have differences. We have differences in how we're structured. We're differences in terms of our funding models and our roles based on how we're funded, as well as our accountabilities. But you just saw a very powerful message in terms of the need for global collaboration in astronomy, but that need also exists on other critical items of humanity like climate change, food and water supply, dealing with chronic illnesses. And so being part of a global organization enabling that is something that we all have in common. And it's that piece that is in common that's probably much greater than where we are different. And it's probably worth maybe talking about how we leverage that. How we leverage that is first and foremost, recognizing that we're all dependent on each other, that the global network requires a loose federation, probably more accurately a confederation of organizations that come together to support global science, global research, global education, and that will come in all kinds of forms in terms of driven by political agendas or government priorities or researcher priorities. And rather than fight the differences, actually embrace the differences, recognizing that diversity is a good thing. We can learn from each other. We can see what's worked in one area and apply that what hasn't worked in other areas and avoid that if we can. And I'll go quickly here because I could speak about this for quite a while. I'm quite passionate about what we do here at CANARIE, as are the other two presidents. But I'll summarize by saying, what's important for the global community is, and I don't mean the global research and education networking community, it's what's important for the people that take advantage of that, is that within the community that we operate, where we're offering connectivity as well as advanced services and identity management and cybersecurity and connecting people, that we recognize the dependency we have on each other. We embrace that dependency. We recognize the diversity. We take advantage of that diversity. And through events like we're having today, maximizing inclusion in a very democratic way. So ultimately, we want to ensure a takeaway for the group here today is to understand that dependency, diversity, and democracy are critical in a confederated system to support the challenges of humanity.
Thank you, Jim. Would you like to add something, Luis, Howard?
I'll echo what Jim said. I think if you look across the NRANs around the world, we have far more in common than I think we actually have. Different funding models and governance models aside, I think we all share the same common goals and have continue to work together to achieve them.
And I will add something, Maria Jose, if you let me.
Yes,
First of all, I am very grateful with my dear friends, Howard and Jim, for this goodwill to cooperate and collaborate, which is something, as Jim mentioned, is in the DNA of the networks, of the research and education networks globally. Actually, we have much more things in common than differences, and the most important, from my point of view, is a widespread and shared practice between these types of network to collaborate in search of the common good. A very important point of view in my thought for a world that is debating today in the false paradox of the individual interest versus the collective goals. No? So I think this meeting and the opportunity we are having today and the collaboration we are expecting to grow soon, much more, is something that shows the kind of humanity we want to have in the future.
Absolutely. I'm going to continue. Howard, how does this collaboration impact research and education communities in your jurisdiction?
No, great question. So, the way I look at it is, every NRAN plays this very important role, providing their community with access to resources, data, and collaborations around the world. And the model for that has been through federations or confederations, as you mentioned. And you think about the network itself is a federation of networks, a network of networks. The Identity and Access Management Federation that we deploy broadly is key to enabling both, domestic and global collaborations. And EDUROAM, the EDUROAM Federation, provides sort of seamless access to visiting researchers. Of course, that was back when people actually traveled and visited each other. We hope we get back there soon. So from my perspective, my community is best served when those federations are vibrant and far-reaching. In other words, the more resources, data, and collaborators that every participant in a federation has, the better it is for all the other participants in the federation. And awareness sort of locally and regionally about all these amazing capabilities, many of the things that great presentations we saw today, is part of achieving that goal and working with us, friends and neighbors on a focused effort to raise awareness of that in the Americas. I think is a very valuable and important next step. Certainly our proximity in space and time makes it a bit easier for these types of collaborations. We'll as we have more of these, I think we'll even make farther progress in demonstrating how important these capabilities are to, as Jim said and Luis said, the not just the specific R&D communities, but all the people that benefit from the research and education efforts.
Good. Luis, Jim, would you like to add something?
Well, I think to Howard's point, I mean, the globe is rather large. We can rather than try to take on the whole globe, I think the three of us have agreed that for our little corner of it, which is largely all in the same time zone, it's we can probably advance things a lot quicker and faster. But also to be a model for just like we talked about from a diversity perspective, in the global perspective, there's also diversity, and they can hopefully learn from what we've done to sort of get a better alignment within the Americas. Because let's not forget that the North and South America are separated by two very large oceans, but are connected north and south. So hopefully through the work we're doing, we can also provide some leadership in the global community.
Thank you, Jim. And Luis, tell me, what is next for the Americas AmRENs? What are we going to do?
It's a wonderful question. Well, I think, first of all, I would like to mention that we are in front of great challenges we are facing as humanity. And it requires everyone's effort to try to solve them. No? COVID-19 showed us very, very clearly that no one is safe if we are not all safe. In this enormous collective effort, science is indispensable, and our research and education networks are a way of intensifying, expanding our capacity to produce knowledge and make it available to humanity. Not for nothing does the United Nations organization recognize the fundamental role of cooperation in the last of its sustainable development goals. I think that CANARIE, Internet 2, and RedCLARA, we share this common vision and the necessary trust between our organization to be able to advance and strengthen these actions. The digital infrastructures that we offer and the capacity that we have to promote an active circulation of scientific communities is something that we hope to make available to research groups throughout the continent. I would like to share some examples that I can offer beside the astronomical example that we look at today from existing collaborations that shows this potential. No? In the field of climate change, for example, it is the All-Atlantic Research Area, which is the result of science diplomacy effort involving countries from both sides of the Atlantic Ocean, which aims at enhancing marine research and innovation cooperation along any and across the Atlantic Ocean, no? from the Arctic to the Antarctic. And you will ask yourself, why is an alliance like this necessary? As stated by the initiative itself, the Atlantic Ocean is an invaluable resource shared by all Atlantic nations and beyond. It requires effective cooperation in marine research and innovation to best unlock its secrets and to manage human activities that depend on it in a sustainable way. The All-Atlantic Ocean Research Alliance intends to advance the shared vision of an Atlantic Ocean that is healthy, resilient, clean, safe, transparent, predictable, productive, understood, and treasured so as to promote the well-being, prosperity, and security of present and future generations. I would like to finish with just another example is in the area of health, which has affected us so much recently. The World Health Organization has promoted the One Health approach, no? Which integrates One Health as a collaborative, multisectoral, and transdisciplinary approach, working at the local, the regional, national, and global levels, and looking for achieving optimal health outcomes by recognizing the interconnection between people, animals, plants, and their shared environment. Our organizations have the capacity to strengthen collaborations with this approach, since they integrate the local to the global, thanks to the 11 research networks that make up RedCLARA, currently covering 11 countries in South America, as well as the networks and connections provided by CANARIE and Internet too. So what we propose as the next steps is to strengthen these articulation capacities between us to better connect our research capacities, made up of scientists and infrastructures, to these great global challenges. All these challenges require all of our capacity. The scientific data and computing capabilities that we provide are essential for this task. But above all that, I think our ability to collaborate and to weave these threads that help us safeguard the Earth, our little spaceship that has cared for us and sustained us for so long. So I think the more important aspect of this activity is that we are beginning a path where we are going to put the capacities we have at the services of our communities in Americas, but also integrating them in a global science challenge that we are facing already. So I would say
yes, we are. Any final thoughts you would like to share with us? Any of you, Howard, Jim, Luis?
I would say one thing I think we heard very strongly today is to solve and to address, these problems, not just the problems that are facing us now and in the future, but also, further the advancement of knowledge and understanding of the universe and ourselves at the end. Not only do we need, people need more technology and resources, but fundamentally, we need more minds that are empowered and capable and enabled to work on these problems. And a lot of those minds, many of those minds are at or in traditionally underserved communities. I think one of the things that we all continue to struggle with and look for ways to address is how do we be inclusive of those underserved communities, and because we need those minds to work on these problems.
I will certainly do. Well, I would like to thank you very much, gentlemen, for your contributions. We are certainly eager to enhance collaboration through our networks and within the entire Latin American continent. Sorry for this Latin. Thank you very much. And to all of you who have participated with us today, We invite you to stay tuned in our communications channels, where you will find all the information of our advances and the future events that we will have during this year. Thank you very much and have a great evening. Thank you.
Thank you.
Bye-bye.
Thank you, Maria Jose. Thank you all. Thank you, Tanya.
Bye.